Hi Year 11, here's our second lesson for the topic of probability. This lesson we're going to look at set theory. So last lesson we learned about probability, including experimental probability or relative frequency, and theoretical probability. And then we learned about compound events and complementary events. So a set is just a collection of objects. For example, these are sets. Set A contains the numbers 1, 2, 3, 4, 5. And set B contains the colours red, yellow and blue. These are called the elements of the set, and we use capital letters to represent the sets. Now we can say that 1 is an element of A. And we can also say that 1 is not an element of B. The empty set or null set has no elements, and there's two ways that we can write it. Curly brackets with nothing inside, or a 0 with a line through it. So here's some familiar number sets that we did cover right at the beginning of the year. This is the set of integers. It has this funny letter Z. So all the way from negative infinity through 0 up to positive infinity. We could even write this. Z with a minus here is all the negative integers. So negative 1, negative 2, negative 3, all the way down. And this is the set of counting numbers, 1, 2, 3, 4, etc. The number of elements in a set is written as n of A. And we looked at this briefly in last lesson when we were looking at the number of elements in the sample space. So if A is the set 1, 2, 3, 4, 5, then n of A, the number of elements, must be 5. A finite set has a definite or defined number of elements, and an infinite set has an infinite number of elements. So for example, Z, which is all of the integers, is an infinite set. Now in set theory, the sample space is called the universal set. It's the set from which the particular elements are drawn. So if I toss a 6-sided die, then the universal set is the numbers 1 to 6. And we write it exactly the same way. Now a Venn diagram is a really nice way of representing sets. A rectangle is drawn to represent the universal set, and then within the rectangle we draw a circle or circles to represent different sets. So let's draw a Venn diagram for the event A that I toss an even number on a 6-sided die. So we have got our universal set here, and within that we have the set A. So the even numbers go inside here, and then the odd numbers will go outside of that set, but still inside the universal set. A subset A of a set B contains some or all of the elements of B. And this is what we write. A is a subset of B. Now for example, if A is equal to the numbers 2, 4, 6, and B is the set 1, 2, 3, 4, 5, 6, then you can see that A is a subset of B. And furthermore, it is a proper subset because it's not equal to. So we can actually write it like this instead of putting the equal sign. And this is what it will look like. We have set B, and inside that we have set A. Now let's look at a couple of operations with sets. Firstly, the union of two sets A and B contains every element in A and every element in B, but we don't duplicate them. And this is what we write. A union B. Here's an example. Given the universal set, which contains the numbers 1 to 10, set A is defined as the numbers 1 to 5, and set B is the even numbers 2, 4, 6, 8, 10. And we want to write A union B. I'm going to start by drawing this as a Venn diagram. The sets overlap because we have common elements. 2 and 4 exist in both sets. Then set A also has the numbers 1, 3 and 5. Set B has the numbers 6, 8 and 10. And outside those two sets are the numbers 7 and 9. The union is all of this. Everything in A, everything in B, and don't double up the 2 and the 4. And this is what we write. A union B is the numbers 1, 2, 3, 4, 5, 6, 8, 10. And then the intersection. The intersection of two sets A and B contains only the common elements that exist in both sets. And this is what we write, A intersection B. Same example, and this time we want only the overlap. So A intersection B is the set 2, 4. Two sets are said to be disjoint or mutually exclusive if they contain no common elements. So here's our example. The universal set contains the numbers 1 to 10. Set A is the numbers 1 to 5, but this time set B is just the numbers 6, 7, and 8. We can see that they are mutually exclusive. There are no common elements. There's no overlap. So when we draw our Venn diagram, the circles are separated. Set A contains 1, 2, 3, 4, 5. Set B contains 6, 7, 8. And 9 and 10 are in the universal set, but not in either of these sets. When we look at the union of A and B, it is going to be just all of these elements added together. So 1, 2, 3, 4, 5, 6, 7, 8. We don't have to worry about double ups. And the intersection is the null set. No elements. And the complement of a set A contains all of the elements not in set A. And we've already seen that this is denoted by A graph or A with a line on top. Now remember, right back at the beginning of year 11, I told you that Q is the set of rational numbers and Q graph is the set of irrational numbers. So there's an example. Here's another one. I toss a 6-sided die. Let E be the event that I throw an even number. Write the set, the complement of E. So if we draw it up, here's the set E with the numbers 2, 4, and 6. Outside of that set, but still inside the universal set, are the numbers 1, 3, 5. And this is the complement of E. So E graph is the set 1, 3, 5. Now there are three relationships between a set and its complement. The first one is that the intersection between a set and its complement is the null set. So let's take our previous example where we had a set A which had the elements 2, 4, and 6, and outside that set, but within the universal set, were the numbers 1, 3, and 5. Now there is no overlap between those two sets. Have a look. 2, 4, 6 here and 1, 3, 5. So the intersection between those two sets is the null set. The second relationship, the union between a set and its complement, is the universal set. And you can see how all of those numbers make up the universal set. And then finally, the number of elements in A plus the number of elements in the complement of A must equal the number of elements in the universal set. Let's move on to Venn diagram regions. We can use set notation to identify various regions in a Venn diagram. Have a look at this first one here. Here we have everything coloured in except for Q. So this is the complement of Q. It's nothing to do with P at all. So we just write Q graph. How about this one here? What's this little bit? This is the intersection between P and Q. And we want everything outside of that. So we're going to put P intersection Q in brackets and then do the complement. And we can get more complicated regions, like this one. I like to call this one the cookie region because it looks a bit like a biscuit with a bite taken out of it. Now I'm going to break this down into two separate regions and show you how to make it. Firstly, the complement of P. See how everything is coloured in except for P? And Q. Everything is coloured in Q. Now have a look what happens when I merge these two regions together. See how the yellow and blue part has become green? That's the intersection. It's the same part here that's coloured in. So this is what it is. It is not P intersection Q, or we could turn it around and say it is Q intersection, not P. Either way is fine. And here's another one. I'm not going to give you the answer to this one. I want you to try and figure it out. Use what we just did. There's a hint. Now in a Venn diagram, there are four regions that we can identify. So if these are the sets P and Q, then the overlap is P intersection Q. This side here, the one that looks a little bit like a cookie, is P intersection not Q. Over this side is Q intersection not P. And outside both of the circles is the complement of P union Q. Now sometimes Venn diagrams don't list the individual elements in each set. They instead show the number of elements. And we could be asked a question like this. Find the number of elements in the set P. So that's everything inside here. 4 plus 3. There's 7 elements in the set P. The number of elements in P union Q is everything in P plus everything in Q, but we don't double up. So we want 4 plus 3 plus 5, which is 12. The number of elements in P intersection not Q, so in P but not in Q, so just this part here, that's 4. And finally, the number of elements in the complement of P union Q. So remember, P union Q is all of these. The complement is outside of that. That must be 3. Let's finish off with a couple of examples of how to construct Venn diagrams from problems. A school has 20 students who study Japanese, 13 who study French, and 3 who study neither Japanese nor French. If there are 30 students altogether, how many study both Japanese and French? So this sort of question is really suited to a Venn diagram, so let's draw that up. We have overlapping circles, the students who study Japanese and the students who study French. Now, as I'm reading through this, I see this. 3 study neither Japanese nor French, so that goes outside the 2 circles. Now the trick here is to add up the 20 students who study Japanese, the 13 who study French, and the 3 who study neither Japanese nor French. And that gives us 36, but we only have 30 students. So there's an overlap of 6. We've double counted 6 students, and that goes here. Now we've actually answered the question, but let's continue and complete the Venn diagram. The number of students who study Japanese is 20, so the number in here must be 14. The number of students who study French is 13, so the number in here should be 7. And a quick check here, adding these up, that gives us 30, so it's correct. Here's example 2. This time we have 3 sets. We have cows, sheep, and poultry, and a whole lot of facts. Now, order is somewhat important. If we have a look at 16 farms have poultry, that's that whole set there, and we can't figure out what the breakup is. So I'm going to start with the very bottom fact. Every farm has at least one of these animals, which means that there's 0 outside of those 3 sets. Now let's look at this one. One farm has cows, sheep, and poultry. That's the overlap here. Now we could do this one, or this one, or this one. Doesn't really matter. Let's try this one. One farm runs cows and poultry, but not sheep. Cows, poultry, not sheep. So that's in here. 1 goes in there. And then we have 6 farms have cows and sheep. So 6 farms have cows and sheep. We've already accounted for 1. This must be 5. 6 farms have sheep and poultry. Sheep and poultry. We already have 1. This must be a 5. And then let's do 26 farms run sheep. So that's this whole set here. We have already accounted for 11 of them. 26 take away 11 is 15. 16 farms have poultry, so that's this whole circle here. We have 5, 6, 7 already accounted for, so that means 9 in here. And then finally, adding up all those numbers, we know that there are 50 farms all up, so this number in here must be 14. And we could be asked some questions about this. One farm is selected at random. Find the probability that it has sheep. So we want all of these numbers here. 15 plus 5 plus 1 plus 5 out of 50, which gives us 26 out of 50. It does not have cows. So everything outside of this circle, 15 and 5 and 9. And that's 29 out of 50. And then finally, it has poultry, but not cows. So poultry, but not here. So here and here, 9 plus 5 is 14 out of 50. We could also be asked to highlight regions in a 3-set Venn diagram. So highlight the region, the intersection of C and S. Well, that must be here. How about not P, intersection S? So in this case, we want the intersection between S and everything outside of P. So it's actually this. So let's just have a quick look at that. So everything in S that is not in P. Does that make sense? And how about this one? S union P. Everything in S and everything in P. Here it is here. And here's a tricky one to finish. Now we've already done this, S union P. Remember that was this part. We want to intersection it with C. So it's got to be common with C. So it's this part here. And finally, a two-way table is an alternate method to a Venn diagram, but it's only ever used for two attributes. So let's return to our Venn diagram about the Japanese and French language students, and we're going to turn it into a two-way table. So we'll start with studying Japanese and French is 6 students. French but no Japanese, so French but no Japanese is 7. No French and Japanese is 14. And no French and no Japanese must be 3. And then all we do is the totals. Okay, that's it for this lesson. Our next lesson is on the laws of probability.